Thank you for inviting me, Cara. Hello, everybody. My name is Chris Angell-Hicks. I have a background in systems engineering and building complex systems for some of our large engineering firms. So previously of BAE Systems and of McLaren, I now work for a company called CloudNC, who are looking to deliver single-click precision manufacturing to the manufacturing industry. So I would describe us as a tech startup based in London, who also have a factory over in Chelmsford, UK. So what I'd like to do today in the webinar is provide a bit of an introduction to myself and to the company, describe the problem that we were facing in our factory, describe the solution we came up with, show you some example results, and then explain how we got there. Okay. So if I start, I'll start by introducing a little bit about what CloudNC are trying to do. So as a company, we are looking to increase the productivity of factories, of manufacturing, through the use of software automation. So we noticed, and our founders identified, that manufacturing is a very manual industry. There's a lot of manual labor that goes into it. It's quite slow, and it takes quite a lot of skill. A lot of this is based on experience and time that particular individuals have spent in the industry learning those skills over time. They don't like to share, and they don't like to teach each other. So one of our key products is a product called CAM Assist, which looks to machine the parts on their behalf. So this is a software automation product that automates the computer-aided manufacturing stage of manufacturing. CAM Assist, we give it a part, and it will come up with the tool paths and the machining strategy to make that part. It'll select which tools to use, it'll select which directions to come from, and it'll define all the tool paths, and it looks to machine as much of your part as possible with one click, embedded within the normal CAM package, so Fusion, NX, Mastercam, etc. We've also developed a product that recommends the feeds and speeds, so the cutting parameters for all of those programs, and that is also embedded within CAM Assist. This looks to automate a lot of the experience that these CAM programmers have developed over time, codifies it, and puts it into our technology. The third key piece of technology, and the one I was going to talk about today, is our Schedule Assist product. This looks to optimize the schedule that you would like to run within your factory in a more efficient way than is possible with a human operator. So we are using some of our optimization techniques that we have developed over time, and we're applying it to the challenge of scheduling work within a factory. So at CloudNC, we believe that the factory of the future is autonomous. We believe that our autonomous manufacturing technology is the heart of the factory. We believe that by using our software automation technology, we can unlock process automation, we can automate a lot of the manual processes, and we can make them more robust and deterministic. We also believe that by using this technology, we can optimize and automate a lot of the dependent stages on that CAM programming, notably the CAM programming and then the machining of those parts. And following on from the heart, as we say here, the autonomous manufacturing technology, is then the optimum planning and scheduling of all of the jobs within the factory. And I'm assuming that not many people on the call are particularly familiar with how factories operate and how we would go about managing our jobs. So I think what I have now, after this slide, is some examples of what I mean by those terms. Before I show you some concrete examples, just a summary of what we're looking to achieve with optimum schedules is this is a piece of technology that reads in the configuration of the factory. So how many machines and workstations we have, the various shifts that the staff members want to run on, the calendars they operate, any holiday they have, any permitted vacancies for training, etc. Whether we have night shifts with more or less people are all fed in as part of the configuration of the factory. We will also feed in all of the commercial aspects of that factory. So all of the orders that we have, the parts that we need to make, and the quantities and due dates of all of those parts and orders. Included in there is what we term the method of manufacture, so how we break down the order into the various stages as it flows through the factory. So ordering of materials, preparing materials, machining, quality inspections, any vendor services that need to be performed are all embedded within that method of manufacture. And finally, we need to also consider what the current stock levels are within that factory. So if we have 5 parts in stock and the customers ask for 10, we only need to make 5 more. And the last piece of information that comes into our scheduling algorithm will be the current operational environment. So the number of parts made for each particular order, the number of vendor orders that have come out for vendor services, and also the new orders of fresh materials that are coming in that would block future work. Coming out of the scheduling algorithm is a plan of all of the additional purchase orders that we need to make. We publish a schedule of where, when, and by whom each job and each job operation needs to be performed. And we also publish a set of key performance indicators, such as the due date for each order. We track the on time in full metric for each order. Ideally, we deliver every single order on time and in full. However, practical manufacturing means that human error, supply chain issues, etc., mean that some of those tend to be a little bit late. And finally, we're also looking at make span, which is a term we use to measure the time between starting a job and finishing that one particular job. And ideally in scheduling, we want to have 100% OTIF. We want to have very, very short make spans and everything to arrive on its due date. Okay. So I mentioned around a method of manufacture. This is one example where a particular job is spread out across the various departments within the factory. So I've listed in the columns each of the various departments for CAM, where CAM Assist would come in, quality planning, material purchase, the setup and machining is setup 1, setup 2, etc. And then we're looking at some quality inspections and then shipping to the customer. The key part of this method of manufacture is I've used 2 different colors to define the 2 different types of work that we're going to focus on today. One of them is the fixed time that occurs once for the order, and the green one is the time estimated per unit. So the green one will scale depending on how many parts we need to make at that particular order. So in this example, we see a green one that's about 7 or 8 rows down, that's about an hour long. To come up with that estimate historically takes a human, where it's called the estimator in our factory. They will look at the job, they will look at the parts, and they will lick their finger, put it in the air, and guess how long a part takes to make. This is not so good in our factory of the future, because we would very much like that estimate to be very accurate. The more accurate we can make that estimate, the more accurate we can make our schedule, and therefore the more parts we can make in a particular time window. So if we move on, this is an example of a factory schedule. The time is coming along the top. The grey bars show areas where we're not scheduled to work. This is, for this example, this is an overnight shift that has no people, and this is a weekend. The blue bars are where particular jobs have been allocated onto the machines. Now, each of these blue bars represents one of the segments from the last graph across the many, many jobs that we have running concurrently within the factory. And to show the level of complexity that we need to deal with, I've highlighted in these red bars some of the transitions between one job and another. For optimum productivity within the factory, we are looking for 0 time between each of the jobs, so 0 time between the job finishing and the next one starting. We also don't want any of the jobs to overrun. So any job that takes longer than we thought has an impact not only on that job, but every other subsequent job that's also scheduled to run on that particular work center. And in the example here, where I've highlighted in purple one of our machines, we can see there's about a 2-hour window between one of the long-running jobs starting and the next one, one of the long-running jobs finishing and the next job starting. Ideally, we want to reduce that down to minutes. And the challenge we had is how can we track our factory's progress to make sure that we know well ahead of time when each job is going to finish, and therefore when will the next one start. Okay, so coming on to the main subject of this webinar, how did Quix improve our scheduling? So in this diagram, I'm showing in the middle our ERP system. So this is a third-party system that we run in our factory that we use to track all of the factory operations. So in the ERP system are all our customer orders. It covers our factory configuration. It covers the shifts and how many people and machines are available in each shift. And it also tracks all of the material that we have available. Coming out of the ERP system is the current tasking that comes down to the machines and the other work centers. And what we've achieved is by inserting Quix into our systems, we can come up with some data that then means we can improve our schedule. And what I'll show you now is some of the results of how that's done, and I'll come back and show you how I achieved that. So in terms of example results, I mentioned first of all, knowing the current state of the factory is really important to us. This graph here is showing the impact that Quix has had on our factory part counting. The kind of bluey, greeny, sorry, I'm not very good at colors, tealy graph here shows how many parts the human operators have told us they've made over time. So they tend to be very bad at counting parts. I'm not quite sure why, but our machine operators are very bad at saying how many parts they've made at any particular time. Typically, they are asked to tell us how many parts they've made at the end of each 8-hour shift. I've actually hidden the timescale on this graph, but this covers about 2 weeks. So what we're seeing here is, although we ask them to count parts and we ask them to declare each time they've made a part, the human operators in this bluey, greeny, teal color have big steps in them, where presumably their supervisors come along, counted how many parts sit on the pallet next to the machine, and have gone and corrected the ERP system. This makes a very challenging situation for our scheduling algorithm, because between all of these various data points, we don't really know how many parts have been made, and therefore we don't really know how many parts are left. This means we have to add significant contingency periods in our schedule to cover the discrepancies. And this is something we wanted to remove because it was causing us trouble. It was causing us to have downtime in the machines, and it was causing us to have an inefficient factory. The purpley chart here shows the results of our part counting algorithm that we developed within the Quix environment. So this provided a much more accurate view of how many parts have been made at any one particular point, which meant we could come up with a much more accurate schedule based on the number of parts remaining in that particular order. And what we see here is visually, around the middle, the human operators even managed to declare more parts made than the machine thought they'd made, which again shows where, if we want to have very efficient factories, we need to rely on the information from the machines rather than the information from people. The second key result that we've achieved is we can also improve the estimated duration of some of these scaling points. So if we think back to the method of manufacture slide I showed a few minutes ago, that green bar is a human estimate based on the part complexity. And in our scheduling algorithm, we take that estimate and we multiply it by the number of parts that are remaining. So any errors in the time duration of the green bars are magnified and multiplied by the number of parts remaining. In this particular example, by using Quix and running some algorithms on the Quix estate, we can show that the machine was actually taking nearly an hour to machine this part, not the 15 minutes that the human had originally estimated. This means we could feed the hour duration of that stage back into the algorithm and come up with a much more achievable schedule that was closer to what the factory could achieve. Again, improving our efficiency, because it meant in this particular example, this job didn't appear to be days and days and days late. And the job that we would have scheduled on the machine after that was scheduled on a different machine and was still able to be delivered on time. Okay, so how did we do it? The first step we took is we applied real-time machine data acquisition. So using some industry data formats of OPC-UA and MT Connect, we could acquire signals directly from the machine, and we could run analysis of them to detect part counting and detect when parts are made. So the development we performed is we wrote a small bit of Python that would acquire the signals from the machine and push the signals to a topic within Qwix. We could then visualize and analyze those signals over time to decide which ones of those were useful and which ones of those helped us understand when parts were made within the machine. And in terms of the impact that Qwix had, we found that by using Qwix, the setup and management of the environment was incredibly easy. It gave us really rapid visualization of the data streams, both live as they came out of the factory and also historically, and also really helped us visualize signals with different data types and different variations on the same graph at the same time. And as an example of the challenges we faced, for one particular machine or one particular controller within the machine, the signals list for OPC-UA stretched to nearly 1,200 pages. So that was a lot of signals that we had to walk through to work out which ones had value to us and which ones were a distraction. The alternative technology of MT Connect, the signals are defined in an XML file. One of them for the machines had nearly 1,000 lines of XML in it. So it was quite a task to discover which of those signals had value and which were distractions. And so for an example 3-month period taken from the Qwix topic visualization, we can see here that the blue signal and the yellow signal provide variation over time and turned out to be very good indicators of what's occurring within the machine. The green signal, although it had a very good name, I think this one was called parts required, we found that it never changed. And therefore it was not a signal that had any value to us, and we were able to stop acquisition of that signal and ignore it. Okay. The next step was to then analyze those signals over time. So using what's now the Stream API, we could receive those signals within a Python script, clean them, run detection of key events, so how those signals change over time, store those events within Qwix with the metrics, and also push key events back into our ERP system ready for use by the scheduler. So key events here would be every time a good part is made, every time the machine is finished making a good part, we could provide a small, we could store that as an event within Qwix and also publish that into the ERP system ready for use in the scheduler. And again, the impact of Qwix here is the environment made application development very, very quick. A lot of the SDK and the other features available made developing those applications, those streaming applications, very, very easy. We could very quickly visualize the results even whilst we were developing them, which made it much quicker. And also the ability to develop the algorithms on our laptops and then push into Qwix for kind of production running made the development, the debugging, and therefore reaching a successful conclusion much, much quicker. And for anyone interested in how we did that, we were using the Git repository within Qwix. And as an example, So on the right, I'm showing some of the data that we would use. So these 4 or 5 signals are fed into one of our stream analytics, and based on this, we can detect when a part has been made by unfortunately trial and error. But we've learned over time how the variation of 3 or 4 of these signals at the same time between 2 timestamps indicates that a part has been made. And in the bottom left, this is an example events that we generate, and the information interesting to us was the timestamp when that event happened, the name of the machine that made the parts, the program name, which tells us the part that it's been made, and then we're looking at some interesting information such as the time and cycle, which is how long the machine has been running for to make that part, the elapsed time that that part has taken in terms of calendar hours, and also the operating time of the machine that part has been taken to make. And these metrics are fed into the schedule to improve our scheduling accuracy. Our last key developments was also looking at batch analytics. So in addition to near real-time detection of part events, we also wanted to monitor the health and utilization of the machines. So for this, we were looking at the data APIs using REST queries limited by dates. And typically we would come up with hourly reports of trends in those areas. So we would query the last hour of data, analyze it in one go, and then write an event with some examples in, such as the utilization of that machine over that hour. And again, as with the stream analytics, the Quix environment was awesome for developing those algorithms. Developing on our laptops and then pushing the signals to and from the cloud made those developments and the debugging super easy. So in conclusion, how has Quix improved CloudNC scheduling? Quix has enabled us to acquire large amounts of data from our machines in near real time. It's provided us with a very smooth and intuitive interface and environment with which to store, visualize, and analyze that data. And it's also provided us the connectivity we needed to push information back into the ERP system and therefore improve our schedule. Okay, so I think that concludes the end of my presentation. Hopefully that was exciting for you. Cara, over to you for questions.
Awesome. Yeah, thank you so much. Really interesting. And maybe before we head to the Q&A, I'll kick things off with a question myself, very selfishly. So you obviously discussed a lot this kind of discrepancies between human operations and automated operations. In particular, you gave the example of the time discrepancies or the estimate discrepancies between the time it takes to make a part between people and what's predicted by your algorithm. So obviously, when you're tackling this in your guys' factory, that is something that's like part of the process. You're trying to evolve your product, but like, how do you see this as a challenge in your customer base or in the wider industry? Like, do you think that everyone is receptive to kind of bringing on board technology that makes things smoother, or is there a lot of resistance?
That's a good question. So I think it's got 2 parts to it. So yes, we found in manufacturing the human error or the human variability involved in estimation is a bugbear. So one of the aspects to CAMAssist, which I didn't really discuss at the beginning, is we provide a cycle time estimate as part of our technology. So by running our code, we can estimate for you the cycle time we think it'll take. So that kind of addresses some of the human variability. However, there's also extra human variability that even if we know exactly how long the program takes to run on the machine, there's still human effort required to load raw material onto the machine, press the go button, wait for the machine to finish, and take the finished part out and put a fresh piece of metal in. So even if we knew exactly how long the program takes to run on the machine, there's still time at the beginning and end for the human to do their piece. So we still needed to track and refine the those time, the kind of total elapsed time, if you like, over the duration of each job.
Makes sense. Then there's a question here, I'll just read it out. Could you share a bit about how much data transformation work was needed to make your machine data Quix ready, aside from digging through the OPC UA data, and whether that was handled at the edge or centrally?
Yes, so fortunately I did very little, or we had to do very little kind of data cleansing before we could push it to Quix. We found Quix was a very tolerant environment to the data we wanted to push in. It seems to be fairly relaxed about data types. Where we did struggle is some of the data from the machines varies over time. So what we thought were strings turned out to be numbers, and sometimes they change between them. So I think from all of the signals we looked at, I think there's about 3 or 4 where we had to run a little bit of cleansing of the signals to make sure they consistently went into Quix. Because we didn't want the data type to change over the schema and over time.
Makes sense. And then there's one more. What factors drove the decision between on-prem and cloud? And how did that impact the implementation timeline? Specifically, was it hard to share data between the factory and Quix? And did you have to kind of involve anyone from security or IT or anyone else in the business?
Being a small tech startup, our IT security was very easy to deal with. Interestingly, we had to run, or I had to run, the acquisition scripts within our factory because the machines we were using had very poor IT security on them. As a computer, they have fairly poor IT security. They don't really have firewalls, and their approach to network security is very behind the times compared to, say, an Amazon web account. So we've very tightly control the information that comes in and out of our factory using hardware firewalls. So I had to install a physical server within the factory so that we could talk to the machines kind of on a trusted subnet, and then that server would then publish out to Quix. But actually getting permission to talk to Quix was very easy, fortunately, because we're a small startup and this is something we wanted to do, so it was quite easy to do.
Makes sense. Yeah, no, we've heard this a lot from our customers, that because all the machines kind of inside the factories have very lax security or non-existent security, then you have to create these like super intense firewalls around the outside, which then makes everything hard. So yeah, interesting to hear how you guys tackled that. I'll give it a couple more minutes in case anyone else has any questions. But if not, thank you very much for, oh, there's one there. How the rework of parts are captured in your schedule assist?
So at the moment we are focused on making the parts for the first time. If a part fails quality inspection and needs rework, typically in our factory that's set up as a separate job, and that'll be estimated separately. And we don't necessarily run the same closed loop processing on the rework time as we would the original parts.
Cool. I hope that answered the question. Otherwise, pop in a follow-up. I'll give it a few more minutes and then we will conclude. But yeah, already, Chris, thank you so much for the presentation. Super insightful. Super interesting to hear a bit more about what you guys are doing. And yeah, great session.
Excellent. Thank you very much.
Amazing. And with that, thank you everyone for joining, and have a great rest of your Thursday. Bye-bye.